We start by writing the famous second law and write A as the second time derivative of the displacement. Now, if the force is a specific force, named a restoring force, it has this form. It has some negative constant multiplied by the displacement. This force will cause the harmonic oscillation, as we'll soon see, causing the body it is acted on to go back and forth through the equilibrium position. As there is some displacement from the equilibrium position, the force wants to restore the body back to it. Notice I chose the equilibrium position at 0 for simplicity. If it was elsewhere, we would need to write instead of x, delta x. So, we get a second order ordinary differential equation. Let's define this as omega. Then the equation takes this form. How to solve it is not important right now. What is important now is to understand that this is the solution, meaning this is what the variable x is equal to in order to fulfill the equation. Take 10 seconds to check it. Substitute here and here this solution and verify you receive 0. The constant A is the amplitude, meaning the maximum value of x, since the maximum magnitude of cosine is 1 and phi is the phase constant. We find those two, A and phi. Speaking about harmonic oscillations, there are two intuitive classic examples. There is a good analogy between them, and I'll try to emphasize it. The spring here going back and forth, and the pendulum, which is a bit harder to understand, having this particle going back and forth in this trajectory. We sketch the coordinate system and the equilibrium position at 0 for simplicity again, and also at the pendulum. Notice that the variable here is x in length units, and here it's an angle. Here x0 is at 0 meters, and here θ0 is at 0 degrees. Since the pendulum makes a circular motion, the coordinate system follows the particle. Next, the force of a spring is minus k, the spring constant, multiplied by the displacement. And here, the force that wants to return the particle to the equilibrium position is the sign of the gravity force. This is the force that pulls the particle back and forth, the sign of the gravity force. So this is the second law, where the pendulum will continue to develop it, because in the end, our variable is an angle, so we need to express our equation with it. This was possible with this equation presented first at the video degrees in radians. Deriving both sides by time, we get the velocity on the circle, and since r is a constant, only theta changes by time, as the particle is moving. We call this omega, the angular velocity, and so forth. Next, this is the force of the spring, and this is the force of gravity on the pendulum. The trick with the pendulum is to work with small angles, small amplitudes, because then we can say the force is mg theta because of this. This is crucial in order to get this form, which we know its solution. If the angle was big, we could not do this proximity, and we would not get this form, and the solution is less trivial, and it's not the point right now. So next, we use this algorithm here, at each side, everyone with its own variable, x and theta, and get here the frequency. Notice that the frequency is not dependent on the amplitude or on the phase, just on the system's properties. For example, the pendulum will swing in the same frequency no matter what the amplitude you give it. So because we have this kind of equation, we know its solution looks like this, everyone with its own variable. Again, if we would not, and more right to say could not, do this proximity, we would not get to this second order ODE, and this would not be the solution. It would be something else, a bit more complicated and not relevant. If we derive the displacement by time, we get the velocity. And if we define this as the maximum velocity, we can write it in this form. The reason this is the maximum velocity is because the magnitude of sine can be maximum 1, so this will be the maximum value that v can be. The same logic goes with the acceleration. Let's look how it looks with the spring. Here is the equilibrium position at 0, and the two edges determined by the amplitude. The box will go back and forth. The spring is invisible, so the picture will be clearer. Let's start from here. The spring is stretched the most it could be, and it gets to a final stop. At this point, the force is the biggest. C is a constant, and so it gets bigger as x gets bigger. And the same with the acceleration. M is a constant, so as f gets bigger, a gets bigger. When x is 0, f is 0, and a is 0. So here, a is 0, and then, as it passes this point, the force to the equilibrium point gets bigger and bigger, and so the velocity gets smaller. T is the amount of time it takes the spring, the pendulum, etc. to go back and forth, to finish one cycle, one circle, or 2 pi radians, or 360 degrees. In the case of the spring, we get by substituting omega that also the time period is dependent only on the physical property. For example, no matter how much you stretch the spring or take this particle higher, the period time will be the same. This is not really intuitive. The total energy, the kinetic energy, and the potential energy is conserved. In the case of a spring, we have half mv squared as the kinetic energy and half kx squared as the potential energy. If you substitute this in here and do one sentence of algebra, you get this amount of joules. You can see straight that at the case x equals 0, we know that the velocity is maximum, and this m will cancel this m, and you get this. And you can check also with the other case, where v is 0, that you get this straight.